Thank you, everyone. I guess it's the last talk of the day. It's 5 o'clock. You've had a long day. You've had a lot of information being thrown at you. So let's talk about something really nice and easy. Let's talk about chaos engineering. I guess before I start, can I just get a quick show of hands? How many of you know what chaos engineering is? Wow, quite a lot of you. I'm really glad. And for everybody else, don't worry. It's just a really nice and easy thing you ought to do. And by the end, you're going to think, wow, this is so simple. Why are we not doing it? So, I've gone through this talk a few times to try to find different icebreakers, and the best one I come up with is, let's talk about smallpox. At least it's not lunchtime, right? So, smallpox was by far one of the deadly diseases that we ever had as a species, until about 1798 when Edward Jenner created the first vaccination. And over 20 years later, we were able to eradicate smallpox at a global scale. So when you really think about it, it is a humongous human achievement. And nowadays, we have vaccination for 25 different diseases. In the UK, by the time you're 14, you've had 20 different vaccinations already. And vaccination in general has become one of the most effective defense that we have against many diseases. And it works, I'm sure most of you are familiar with how vaccination works. It works by injecting you with a small amount of the disease, so not enough to make you sick, but enough to give your body the chance to react to it, to understand what's this thing, this foreign virus, so that you can start building defense against them before you get into contact with the disease for real. And that's where you can draw a lot of parallels with the practices of chaos engineering, whereby we use experiments to inject small amounts of failures into our system deliberately, not enough to take the whole system down, but enough for us to observe and see how our system fails when those failures most happen, enough so that we can understand how the system behaves before those failure modes actually happens in production in a completely uncontrolled manner, so that we have time to build defense against them. And over time, we can build confidence in our system's ability to withstand those failure modes because we've taken the time to see and learn about how the system fails. So my name is Yan. I'm a principal engineer working at the Zone, and it was announced this week that I'm also an AWS Serverless hero. Yay! Trust me, you probably now, but I'm going to be working this for so many years, so by the end you're going to be so sick of me telling you. So the Zone is a subscription platform that allows you to watch sports on demand as well as in the live stream. That's why we call ourselves Netflix for sports. Right now, we have so many different sports and leagues available on the platform, and we just signed up the Italian league and the box in the US as well. We are available in 5 countries, and Italy is coming up pretty soon. And we're also available across different platforms, mobile and some TV set-top box in Japan as well. And at peak, we have over 500,000 concurrent users all coming to the system in about 1 minute time before the match starts, as you do. So there is some really interesting scalability and technical challenges involved as well. So if that's the kind of thing that gets you interested, we are hiring very aggressively in multiple locations. So come check us out at engineering.thezone.com or follow us on Twitter to see what's going on. So chaos engineering is something that I care a lot about because this is a system that's going to be used by so many people. We need to make sure that it's really resilient against many forms of different failures. I've been doing a lot of reading around chaos engineering, and I love the things that the Gremlin guys are doing in terms of building a commercial platform for you to do chaos experiments yourself. But whenever I see blog posts like this with a title such as Breaking Things on Purpose, it does worry me a little bit because it puts so much emphasis on the act of breaking something. So as someone new coming into the field, it's easy for me to confuse the action with the payback, because when we do chaos experiments, the goal is not to actually break production. The goal is so that we can do a small amount of failure so that that allows us to learn how our system behaves so that we have time to build resilience against those failures while they're still, before we actually see them happen in production. Just as the point of vaccination is not to actually give someone a disease, right? It's about injecting you just enough of that disease so that your immune system can become active and build defense against that in the future. And if you go to principlesofchaos.org, you can also find a very nice documentation around what it is what we're trying to achieve with chaos engineering, as well as 4 simple steps that you can follow to start doing chaos experiments yourself. The first step is you need to define what good looks like, what does normal working condition look like for your system. So this is where if your system is on fire all the time, then you don't have a steady state and you're not ready to do any of this chaos experiment stuff. Instead, try to focus on making your system stable first. Now you understand what normal looks like, then you can start to hypothesize different scenarios and how your system would behave in those scenarios. And then when you identify weaknesses, then you have time to build defense against those failure modes. There's also a lot of space for you to just try something that you have no idea how your system is going to behave, and they're really good for identifying weaknesses or unknown unknowns. So how would your system behave if, say, DynamoDB goes down tomorrow or S3 becomes unavailable for many hours? So those are things that we don't typically think about, but again, when you want to build really resilient systems, you have to see how your system behaves and start building defense against those kind of failures. But those kind of exploratory experiments, you probably shouldn't do them in production right away. Again, the point is not to break production. So for those kind of experiments where you have no idea what's going to happen, try them in an environment that's outside of production, like a staging environment where you've got a production-like setup, but any sort of unintended fallout is going to impact your users. By the time your experiment is ready to graduate to production, you should have a very good confidence that whatever failure that you're going to introduce, your system can actually handle it. And you get that confidence by repeating those experiments in an environment where the stakes are lower, where you can safely break things and just understand them and then build resilience. Because I'm going to keep saying this, that the goal of doing chaos experiments is not to break production. And if you know something's going to break, for example, if I'm using DynamoDB or my critical path and I know that if it goes down, my system is going to go down, there's no point running those experiments in production, because if you do that, you're not going to learn anything you didn't know before, and also all you're going to do is you're going to make your customers angry unnecessarily. So now that you've decided, okay, these are the scenarios we want to see, we want to run this experiment, how do you then go about injecting those failures? The most well-known tool to do that is Netflix's Simian Army, and Netflix also written a very handy free ebook that you can download that talks about how the engineers at Netflix approaches conducting these experiments, both from a social side but also from a technical side as well. And I mentioned these guys earlier, Gremlin, so they built a commercial tool that allows you to schedule and automatically execute some of those chaos experiments and also produce reports so that everyone can at a glance see what experiments people are running and what's the outcome, what's the learning. And when you're running those experiments, you want to be collecting metrics so that at the end of that, you can look at those metrics to try to prove or disprove your original hypothesis. And if you're able to identify weaknesses that you didn't know about before, then great. Now's your time. Now you've got a time to actually then go and do the engineering work to make sure that your system is resilient to those kind of failures. And since these experiments need to be controlled because we don't want to break production, so we need to think really carefully in terms of how we conduct these experiments to make sure that they are, in fact, under control. And one of the most important things we have to do is that we want to communicate to everyone involved what we are doing. So if you're going to run experiments that are going to impact some other team's system, then you should make sure that they understand what you're doing, they know it's coming, they're ready for it. It should never be the case that I come into the office one day and see my dashboard and everything's red, and it turns out that the Thomas or someone else is running an experiment that's taking down my system. I mean, that sort of thing should just never happen. I should know exactly when you're going to do something and what you're going to do, and that I should be ready for any unintended fallouts. And that brings us to the timing of when you run these experiments. You definitely want to run them during office hours when people are in the office, and if there's any unintended fallouts happen, at least we have people in the office to deal with them. You shouldn't have to force people to wake up at 2 a.m. in the morning because you're running some stupid experiment that breaks down other people's systems. Another thing to keep in mind is that if you've got important launch days coming up, don't go anywhere near those important dates. You don't want to go to the business and say, "Oh, I'm sorry, you guys launched the Daredevil Season 3, and people can't watch it because we run some experiment and unintentionally we broke the system. Sorry, guys." That just should never happen. And finally, containment and blast radius should be in the front and center of your thinking. This is especially true if you plan to run those experiments in the production environment, because again, the point is not to break production. And you do this by doing the smallest amount of change possible that allow you to detect or to prove or disprove your original hypothesis, but not enough to actually unintentionally taking down your entire system. And you should also have a rollback plan ready as well. Should anything unexpected happen, just stop the experiment right away and roll back. So you hear a lot of big companies like the Amazon and the Google, the Netflix in the world doing these experiments constantly in production, but it's worth keeping in mind that even those guys, they didn't start in production right away. In fact, there's so much learning you can make by just running those experiments in a staging environment where you have got a production-like setup that allows you to simulate some of the similar failure modes without running the risk of impacting users in production. And as Ross Miles keeps talking about, that chaos engineering is not just about stress testing your infrastructure. It can be applied to other layers of the social technical system we use for software engineering as well. And Ross is really great at communicating the social side of things. In fact, one of the most important lessons that I learned from Ross is that when you talk to the business users, don't call it chaos, because that gives a really bad vibe. Instead, you should call it what it actually is, which is continuous resilience testing. And when you frame what you're doing in those words, it makes a lot more sense for a business to understand what your end goal is, rather than, oh, this guy just want to break production. What the hell, right? So we talked about the Simian Army tools earlier, where you have latency monkey that can induce arbitrary delays into APIs to test what happens if one of your dependencies is really slow. You've got Chaos Monkey that kills EC2 instances randomly, and then you've got Chaos Gorilla that kills entire availability zones in AWS, and finally, you also have Chaos Con that just knocks out an entire AWS region. And I've also seen quite a few attempts at wrapping the logic of Chaos Monkey into Lambda functions, so you don't need to run an EC2 server just to kill other EC2 servers. But what I'm really interested in is how do we take some of the learnings and the principles that we apply with chaos engineering and make them work for Lambda, whereby there is no server that you can access, and therefore there's nothing that you can actually kill. But then again, the principle of chaos engineering is not about killing servers anyway. It's what we do because when our infrastructure is entirely, well, mostly running on EC2 instances, and the most likely failure that we are going to face is a server going down or a server becomes unaccessible. But chaos engineering itself is about identifying weaknesses before they manifest in system-wide aberrant behaviors. And we shouldn't confuse the principles with the action that we perform in order to apply those principles. And in one of my previous companies, I worked on an untrivial serverless architecture whereby we migrated a social network to run more or less entirely on serverless. And one of the things I learned is that when you have a serverless architecture, there is just so much more inherent chaos and complexity in the system that you're working with. You have a much smaller unit of deployment, which is a great thing for very many reasons, but you also end up with so many more of them as well. And that means now you have a lot more boundaries that need to harden around, because before you can harden around individual EC2 instances, but now you have to do that for every single function that makes up your application. Another thing you notice a lot of guys talk about when you're doing serverless is that we don't want to manage servers altogether. Doesn't matter whether it's for our compute or is it for our databases. If we don't want to run servers or manage servers for the things that I'm doing to provide the value for my customers, why would I want to do that to run databases and other things I use as well? So we tend to use a lot more intermediate services, and we also see many Lambda functions being chained together by these intermediate services as well. And the thing about having all these intermediate services in our system is that each one of them has got their own failure modes as well. Some of them are documented, I'm sure, but many of them will not be documented. And even the things that are documented, we don't really have a way to be sure the documented behavior would actually be true until something actually happens. Another thing you find is that with Lambda functions, and I guess similar to IBM Cloud Functions and other Google Cloud Functions, is that every single individual unit of deployment now need to be configured correctly from the point of timeout settings to permissions and so on. And then there's everything the platform does for you in terms of scheduling containers, scaling, polling kinesis, and calling your functions, or retrying fail invocations and so on. All of those features have got their own set of failures modes as well. And again, because those are all just black boxes, any failure modes we may run into might not even be documented. And when something does happen, you lose, now that you don't have control of the infrastructure, there's oftentimes we don't have any way that we can deal with it other than just wait for Amazon or whoever to sort out the problem. For example, if tomorrow there's something happens between Kinesis and Lambda, since we don't have the state for the Kinesis polar, we can't just move our Kinesis processing logic to something else. We just have to wait for AWS to sort out the problem. That said, there's still a lot of weaknesses in our own code that we can run experiments to identify, and then there are known ways to fix them as well. For example, maybe when we're talking to other services, we're not handling timeout conditions gracefully, or maybe there are missing error handlers, and in cases where we can apply a fallback should the downstream system we're using becomes unavailable, maybe we're not doing them wherever possible as well. And for me, the most common issue running into production tend to be performance-related, or rather latency-related, which can be symptomatic of a whole host of other issues underlying, which could be Amazon's networking issues, or it could be I'm talking to a server that is overloaded, or it could be hitting a server that's just having to have a really long garbage collection cycle. So if I want to apply the same 4 steps, step 1, I want to define what good looks like for my system. So I need to decide what metrics make sense for my experiments. Some good common candidates include 95 or 99 percentile latency numbers, or error count, or the percentage of requests that I was able to complete. And then in order to hypothesize how my system would behave, there's a couple of things I need to consider with regards to serverless or AWS Lambda. For example, when you're building APIs with API Gateway and Lambda, one additional thing to think about is that API Gateway has got a timeout, a hard limit of 29 seconds. So your function can run for 5 minutes, but API Gateway is going to time out after 29 seconds anyway. Another thing to think about is the effect of cold starts. So I've got one API calling another one. Both of them are configured by me, so I know that a second function has got a timeout itself of only 3 seconds. But in practice, when I'm calling this second API, I can experience the response time much longer than 3 seconds by the time I factor in the overhead the API Gateway introduces, but also the effect of cold start on that second function as well. And when it comes to timing out API calls, the rule of thumb in microservices is to use short timeouts. And your strategy for this, the goal of your timeout strategy should allow those HTTP requests the best chance to succeed. At the same time, it should, but not at the cost of causing the calling function to also time out an error and therefore starting a cascade failure in the system. And that's where I find that when you try to choose the right timeout value, it's really tricky. They can be too short, so you're not giving those HTTP requests the best chance to succeed. At the same time, they can also be too long, so when the downstream system is slow, it's now causing your calling function to also time out an error before you have a chance to apply some clever recovery, like using a fallback value and so on. And it gets much worse by the time you have a function that needs to make multiple API calls, which is quite common. You've got an API that needs to call DynamoDB to get some data, do some manipulation, save the data back into DynamoDB, and then it's going to publish an event into Kinesis to tell everybody else that, hey, I've just created a user, and so on. And I see 2 common strategies, and both of them have got pretty obvious shortcomings. So suppose you've got a function that's got 6 seconds of timeout itself, and it's making 3 API calls. So one strategy is to divide your API calls timeout-wise so that each one has got a 2-second timeout. So in this case, even though overall I've got enough time to make all 3 API calls, but one of them was slower than usual, so that gets timed out instead. So I'm not giving all the requests the best chance to succeed. Another strategy I often see is that, okay, I'll be more optimistic instead. So I've got a function that's got 6 seconds timeout. So everything I'm calling, I'm going to give it 5 seconds. So hopefully that should be enough for everything. And in this particular case, you see that I've got 3 API calls. None of them are very slow, so none of them get timed out. But overall, together, they take longer than 6 seconds. So end up causing my function to time out instead. So one easy thing you could do instead is to set your timeout when you're making an HTTP request dynamically based on the amount of time you actually have got left in the invocation, which in Lambda, you can actually find it easily via the context object your functions is invoked with, which you can call context.get remaining time in milliseconds if you're running a node to find out how many milliseconds is left in the current invocation. And in this case, I can have a very simple scheme whereby I always reserve some amount of time at the end for recovery, and then any API call I make in the meantime will be given as much time as available in the current invocation. So even if one of them takes longer than usual, fine, it gets timed out, but I still have some time left in the end to do recovery, which include doing things like making sure that I log the timeout incident with as much context as possible. What URL was I trying to call? What was the timeout value? Maybe even any correlation IDs I've collected so far, as well as the request object I've used as well. And also want to record custom metrics for these timeouts. So if I'm talking to system X, it could be system X.timeout as a count metric. I can also use the fallback pattern, which is actually baked into the histories library by Netflix. For example, if I'm reading from DynamoDB and DynamoDB happen to be slow and I have to time out the request, if I've got a previously cached response, I can also use that, or failing that, I can also potentially use the default value as well. And in fact, that's exactly what happens when you go to Netflix's homepage. They always try to load your personal profile so that they can create a rail based on your watching history, which I was watching Benji. No judgment, please. So if what was I saying? Right. So if that system fails or is really slow for whatever reason, then they will try to return me from that server. If they got a previous cache response from that system for me, then return that. And failing that, they're going to return me the default rail that everybody sees, which is not going to include Benji, unfortunately. So that's a very common pattern you apply, whereby you trade precision of your answer for availability. And that's a very good choice for many cases, but at the same time, if someone is trying to check their bank balance, maybe it's not the best thing to do to show them a default value or even a stale response from yesterday. And so imagine you come into your bank account and see you've got 0 money left, and the first thing you're going to do is going to call customer support. So even though sacrificing precision for availability is a good choice for many, many cases, you still have to keep in mind of the user experience. At the end of the day, that's the most important thing you've got to think about. So then how do we inject the failures into our Lambda functions? So suppose I've got a very simple setup here of 2 user-facing APIs, each one of them with API Gateway and Lambda, and both of them is talking to some internal API I have, which is also written with Lambda and API Gateway. And the hypothesis is that, say, public API A is handling timeouts from the internal API gracefully, so that it's able to, say, use the fallback value instead. So to inject that failure, I can inject latency into the HTTP client that my Lambda function is using to talk to the internal API, so that this way I can simulate what happens when the internal API is being slow. And we should also do the same thing as well when we talk to other services, such as the DynamoDB or anything else that we depend on. So for the case of AWS services, we can inject latency into the AWS DK directly. So in terms of the blast radius for this experiment, is because it's only touching the edge services that are user-facing. So it's whatever problem is going to happen is going to be limited to that particular service, and you're unlikely to cause a cascade failure that's going to impact many parts of your system at the same time. So that's good. But we can also broaden the hypothesis around having appropriate timeout handling for anyone that's talking to this internal API. So another thing we could potentially do is to inject latency into the Lambda function behind the internal API directly. In this case, you're going to impact all the different services at the same time. All the services that depends on this internal API. So now you have a pretty big blast radius, and it becomes a bit risky. So for things like this, you probably don't want to run them in production, because again, the point is not to hurt production. But they can actually be really effective at reading out weaknesses across many, many services at the same time. So you should consider doing that in an environment that's outside of production. And then there's also another good argument, which I'm going to make now, for why you should do them in the dev environment constantly as well. Because one thing that we tend to fail often and all the time is that we're not priming our developers to think about failures early enough. Suppose you're working on a new project, you're working against a development environment where everything is nice and easy, nice and fast, because you just don't have any load. You never have a dev environment that's always under load, so that you don't see a lot of performance latency issues related to load. But the moment your system is deployed to production, you're now operating in a completely different environment altogether. You can't control how your users comes into the system. They're all going to come in at the same time. They're going to flood your application, and you're going to see all kinds of latency problems that you just never experienced in the development environment. In psychology, we got this technique called priming, whereby we can subtly manipulate the way someone behaves and thinks by consistently projecting them to a same set of stimulus. So when Facebook is trying to get into the Asia market where network bandwidth is much more limited, they had this whole thing called the 2G Tuesdays, whereby on every Tuesday, they would turn the office Wi-Fi down so that it simulates what 2G feels like, so that as developers working on Facebook, I'm constantly reminded of what someone would feel when they try to use Facebook on a 2G connection. So that makes me constantly think about, even when the Wi-Fi is now back to normal strength, of what that would look like when someone uses Facebook on 2G. So this kind of experiment that can impact many systems all at the same time can actually be quite good when you apply them in a dev environment for, say, a small percentage of requests. Maybe 1% of all requests will have some latency being added, or maybe a small percentage of requests will always fail in the dev environment, so that as a developer working against our internal systems, I'm always exposed to the fact that they can be slow, they can fail, so that when I'm working against those systems, I'm constantly trying to build resilience into my application without having to rely on something that we do after the fact. And of course, the client application is also an important cog in the whole system to make sure that we give our users the best experience as possible. So we should also do these kind of experiments at the client as well. And you can do the same thing by injecting latency to the user-facing APIs directly, in which case, again, you're doing this at the edge services, so the blast radius is relatively small, but you can also inject latency directly into the HTTP client that's used by your client application as well. And of course, when you're running experiments, you're collecting all these different metrics, and at the end of it, you try to go through the metrics to look for evidence that the failure that you were injecting, in this case, latency you're injecting, has impacted the end-to-end experience that we give to our users. How do you then introduce inject latency then? If you're talking about static language like Java or C#, you can consider using a static weaver like AspectJ for JVM or PostSharp for the .NET world. But for Node.js and other dynamic languages, you can also consider using a manually crafted wrapper library as well. So when I ran an experiment recently, I did this by creating an HTTP client that has got a very simple method to inject some latency based on configuration that allows me to control when to do this and also how frequently I do that as well. And then I just use Bluebird's delay function to actually add a small amount of latency to the HTTP request. So in my HTTP client, I've got a very simple method that takes the HTTP request object, and which includes the configuration, which I then use to control my experiment on when to inject latency. And the configuration ultimately comes from SSM parameter store. And in this case, in order to see the latency being injected so that when I run the experiment, I know what's going on, I turn the probability all the way up to 50% of a delay between 100 milliseconds and 5 seconds. And everything was hooked up to X-ray, so I can see that what's happening as well. And in one case, I see that this HTTP request was really fast because no latency was injected. On a separate request, I can see that 3.4 seconds was added to the HTTP request from using my wrapper. So that's all well and good for a very simple HTTP client that essentially just got one method. What do you do when it comes to say, AWS SDK? What you can do in that case is you can take a leaf out of Bluebird's promise file all function to the factory function. And in this case, I've got a badly named injectable all method, which takes a promiseified AWS SDK client and hijacks the get async function so that I can take an additional parameter. In this case, it's the same config value that you saw earlier, so that I can control how much latency to inject when I talk to, say, DynamoDB via the AWS SDK. And in this case, I can see that I was able to inject 1.4 seconds to my call to DynamoDB. So what that experiment is nicely wrapped inside a GitHub repo. You can check it out yourself. But we don't have to stop there. There's also other experiments that we should consider doing as well. For example, the most common error that I run into when working with DynamoDB is the read or write throughput exceeded exception. And that's something that we don't tend to often deal with ourselves. We don't tend to think about it often until we actually see it happen in one of the in production, most likely. So what you could do is you can apply the same technique to inject specific errors. So when you're working with AWS DK, so you can also see, okay, as when we run this experiment, we're going to inject that particular error. And also there's also other things you can do. For example, if you want to see what happened to your serverless application when they're not able to talk to DynamoDB because DynamoDB is unavailable for whatever reason, then you can also, during the experiment, change the IAM permissions for the function that you want to target and just disable its access to DynamoDB to see what happens when that function loses access to DynamoDB altogether. Another common problem that we need to think about when it comes to Lambda is what happens when our Lambda functions are throttled? Because there's a regional throttle limit that applies to all functions. So really, it can happen to any function at any random point in time, and it's something that we don't tend to think about much at all. So one thing you could do then as the experiment is to change the concurrency setting for that particular function to something really low, so then you can start to see, okay, what happens to that function what happens to the rest of the system when that function is getting throttled? Does we not have like a cascade failure that's going to impact many parts of the system at the same time? So I'm running out of time here. So the message I want you to take away is the fact that failures are inevitable, and the only way that we truly know our application is resilient against those failures is to put it through the test using controlled experiments. And through these experiments, we learn about our system's weaknesses before they actually happen, so we have time to actually improve it and build confidence in our system's ability over time. Unless, of course, you just jump the gun and decide to go straight to production and break things, and you can be sure that no one in their right mind will ever let you go anywhere near production with your fancy chaos experiments ever again, so don't do that. And with serverless technology on AWS Lambda, we had just a lot more inherent chaos and complexity in the system that we're dealing with. If anything, we have a much greater need for better resilience and better understanding of our weaknesses than before. So you should definitely apply principles of chaos engineering and try to vaccinate your Lambda functions against failures. Once again, my name is Yan, and if you want to find out a bit more about what we're doing at the Zone, there's a lot of guys you can see walking around in the place and ask them about what's going on. And thank you very much for your time.